Okay, so welcome. So let's get started. Today we will continue to talk about the direct methods. We have the same logistics to update, except one thing. So in terms of homework, quiz, exam, videos, tutorial videos, you make sure make a copy of them. And then we have the guest lecture on September 26th. Those are all the same. Only one thing, I moved this is updated schedule. I only moved the time you can watch the tutorial to after the exam number 1, because those videos will be useful for the project. And for the exam number 1, we will only talk about, we will only give the questions regarding to simple mathematics, direct method, and the material to be discussed in the next few lectures about the uniaxial bars and the truss elements. But those questions to be included in the exam number 1 will be also some similar question will be also in the homework number 1, number 2. So you make sure you do the homework well, and then you will have no worry at all in the exam. Okay, can you guys hear me? Very good, Andrew. Very good. Good. And also, I heard several students actually emailed me saying that they actually have infected by the COVID. So I want to urge all of you, be very careful. Okay, be very careful and take great care of yourselves. Okay, so make sure that you are healthy, and then we can have a great class during this semester. Okay, together. Yeah. Okay, so not many changes in the logistics. So I think you guys are doing great, and I received many surveys after the class. Very positive. That's excellent. So it seems you guys are doing well. And then we will keep the current pace. If there are some, if you feel you want me to slow down, or you want me to speed up, let me know. I can do that for sure. Okay. So currently we keep the same pace, and I wanted all of you to have a great learning experience. Okay. Very good. So let's go to the materials now. So last lecture, we talked about the direct method, right? So just a brief review of direct method. So this system, this picture, do you guys see my mouse? Let me change to the laser point. Yeah, good. Very good. So I have a question there. One is the first quiz. Kelly asked this question. Good question. So first quiz we will give in about 1 week. Okay. So you will have the quiz, but that is not relevant to the exam. So we will give you the first quiz. I will give you the heads up earlier. Okay. So no worry about that. So good question. So this system showing on the top is a 1D system of the springs. It said 1D means all the force deformation are around one direction. In this case, it's around the horizontal direction that by default is X direction. Okay, and then in this case, in this system, in this 1D system, we have 3 major components. One is rigid wall, which are rigid walls, which are at the left-hand side and right-hand side. They cannot be deformed at all. They are connected with the spring, with a spring, and they can sustain force and generate a reaction force to balance with this force. But they cannot deform, means at the point that the spring connected with the wall, there are no displacement. Okay. Second component is the spring. So those are spring, like number 1, 2, 3, 4, 5, 6. We have 6 springs in this 1D system. Those springs can deform, can also have sustained force. Okay, but this spring and this spring actually is called element. They are called element. Okay, those springs, different springs are connected together through some rigid body. Rigid body. This rigid body can move. They can move. This is called a node. Called node. They are actually a connection point between different springs. They can move, and also force can be applied on it. But it's called a rigid body, so this itself cannot deform, and it can sustain force, and the force on the rigid body actually balance with each other. So there are no net force if you summarize all the force applied on any rigid body, any node. So that's called a node. And usually we use the annotation, the number enclosed by the circle to denote rigid body like node. Wall is also rigid. Wall is also rigid, but it cannot move. It has a zero displacement, but it's also can be regarded as a node, and this node has the displacement equal to 0 boundary condition. Okay, so overall we have 3 components. 3 components, and they actually can be categorized into 2 groups. One is called a node, that including the wall that cannot move, and this rigid body connected with multiple springs but can move, right? So 1, 2, 3, 4, 5. For those nodes, we have the number enclosed by circle to denote that. So in the future, when you see those symbol here, you will know this is actually the node. For the spring, that actually is called element. This is the element. Those spring, we use the number to denote that. Okay, so in fact, in the finite element method, this system is actually already discretized because you have individual elements here now. Okay, if you in the future, if you encounter the question that has a continuous body, then using a finite element, you can discretize that into different pieces. Each piece is an element, and elements are connected with the node. Okay, and those elements you can regard them as a spring. The element can deform, can change the shape, but there are no external force applied to the element. Okay, element can generate its own internal force, but no external force applied to the element. And then elements are connected with the nodes. Those nodes cannot deform. They are rigid body. And then, but the nodes can sustain external force applied from the environment. And it can also be subjected to internal force coming from different elements connected to it. And then those external force, internal force summarized together, they are in equilibrium, they equal to 0. Okay, so in the future, when you study the continuous material, you can do it in similar, and that can be generalized into this kind of system. Okay, here we just show 1D system, but it can also be 2D, but the principle is the same. Okay, very good. So also for this, you see those moving rigid body, they actually sustain. They are subjected to external force F2, F3, and F4. Here, 2, 3, 4. Those subscripts means force is applied on this number, on this node, have those corresponding number. Okay, that's the reason. And the whole system are in the equilibrium. Now, once we understand this the organization of the system, then we can start to analyze the system, because we know some force here, but we also have many unknown in this system. Can you guys hear me? Yeah, excellent. We also have unknown here. First unknown is we have those rigid body, rigid wall. They are sustaining the force applied through spring 1, spring 4. And for the wall number 5, it is subjected to a force applied through spring number 6. So what's the force that those walls generate to react with those external force? I mean, external force is with respect to this wall. In the whole system, this force is generated internally in the spring number 6. Okay, here over the whole system, external force is only F2, F3, and F4. Okay, so there are also force generated by those walls to keep it balancing with the spring force. What are those forces? Those we don't know now, and we want to find that out. Okay. Other unknown is how big is the deformation of each spring when these 3 external forces are applied. We want to know what's their deformation. Then we will know the whole system, how the whole rigid, how the continuous body get deformed in each different point, right? So those are unknowns. There are also other knowns here. And those knowns are this spring. We know their spring constant. We know how rigid, how soft, how flexible are those springs. That we know. So the material property of the springs are known. External force are known. The alignment, the assembly, organization of those components are known. Okay. So now we are very clear what is known, what is not known. And then let's go set out to solve those unknowns. So to solve those unknowns, last class we discussed about a method that is called organizing connectivity map, connectivity table, right? Sometimes called a connectivity map, but it's the same thing. Now, to do that, we firstly look into the every component in the system from left to the right. Follow this convention, okay? And this convention, and also you may notice that all this number actually is assembled in that way. You see from 1 to 5, those are 5 rigid body. They actually are assembled from left to the right. And also the 6 springs from 1 to number 6, they also aligned from left to right, right? That's the convention to help you to organize connectivity table more precisely. So in this table, we will have the raw number the same as the element number, because in the finite element is most important. What do you want to find out is actually the element deformation, okay? And then to find out the element deformation, we need to know what's the force applied there. And those force need to be resolved by understanding the external force and the relationship between external force and the connectivity of different elements. So we write, so the raw number equals to the element number. And then we need to write out the node information for each element. For example, for element number 1, it has 2 nodes because this is the 1-dimension problem. So it only has 2 nodes, left and right. It has node number 1. For here you write the node that enclose the element from left to right. So for the element number 1, the node is 1 on the left, 2 on the right. For the element number 2, the node is 2 on the left. So this element node is number 2 on the left, 4 on the right, right? Number 3 is number 3 element, number 3 spring, node 2 left, 3 right. This one 3, right? Number 4, this guy, 1 on the left, 3 on the right. Number 5, 3 left, 4 right. Number 6, 4 left, 5 right. I go through this in details so that you get familiar with the way to construct this connectivity table. In the future, in many homework problems, exam problems, we will reassemble those springs and the rigid body. Then you can use the same way as I just discussed to assemble their corresponding connectivity table. It's the same way, but just a different assembly. Okay, this table is very useful. It can avoid many confusions. Okay, so with this here we know that in this specific 1D system, we have 6 elements, 5 nodes, and they are assembled in this manner, right? Then we can start to look into element one by one. So in last lecture, we actually already discussed how to understand the single spring. So here I just very briefly go over the key point. So firstly, here is one spring. We name it E to be generalizable. Okay, we call it E. On the left-hand side, it has 2 rigid body connected to it, right? So 2 rigid body, that we also call it node rigid body, is right as I encircled with enclosed with circle on the left, and J enclosed with the circle on the right, I and J. And then E, you see E, we don't have any circle around it. It means this is an element, right? This is a spring. Now, we on the force only applied on the node, not element. So in this case, we can find out the displacement of those nodes and the force of those nodes. We denote this. We denote that on the node I as UI is the displacement of this node. FIE is the force applied on this node, and this node belongs to spring E. Okay. On the other side, we have displacement UJ. We have a force FJ E. J means the force on this node, but related to this spring, E spring. Okay. Right now, we assume all the force, all the displacement are from left to right, positive, around the positive X direction. You can assume this direction. And then when you do the calculation, put the numerical number in to the calculation, you will find that the value is positive sometimes. That means the assumed direction is correct. That, or sometimes you find the value you solve is actually negative. That means assume the direction is wrong. We should go, the real direction is opposite. That doesn't matter. It will tell you that the direction is opposite. Then you just change the sign there. Then you just write the displacement number, force number to that node. That's fine. Okay. Now, within this spring, these two forces, Fi and Fj, they actually are applied. If you look at the system here, small mini system of a spring, these two forces actually are in balance. They are applied, they can be viewed as the external force applied to this small spring. They are actually equal to each other in terms of magnitude and opposite in the direction. So that Fie plus Fje actually equal to 0. Here, we write the equilibrium here. That means they are the inverse of itself. Okay, very useful, very useful. And then this force can also be calculated. They can be because they are balanced by the internal force generated by the spring. So internal force of the spring can be calculated using the Hooke's law. We first need to know the deformation of this spring, and then we already know the spring constant of the spring. Now multiply both together. Then we will get the force generated by the spring. Okay. So to know the deformation of this spring, we actually follow the convention from the right-hand side minus left-hand side using the displacement, net displacement. And then displacement Uj minus displacement Ui actually is the movement of this point minus movement of this point. If they have difference, that is the net deformation of the entity between them. If they have no difference, that means that the entity in between them actually is not deformed. The whole thing is performing rigid body movement, rigid translocation. Okay. Now, if Ui is larger than Uj, then that means this displacement is larger than this displacement. Then the spring is actually elongated. So once it's elongated, they actually want to shrink back. So they will generate a tension force. They will generate, actually inside, they will generate an internal tension force, and they want to pull the node back. Okay. Now that force can be calculated by multiply spring constant Ke. K is spring constant. E is the spring. So that means the spring constant of the spring E. Then times that net deformation. It gives the net force. This PE is the force in the spring. E is the spring E. P is the PE using this. Okay. So that's the convention. You need to get familiar. You don't need to memorize it. Once you encounter it and use it for many times, you actually get familiar with it. It's very systematic. In the future lectures, we will use the same convention. Very useful. And once we have this force PE, it actually can be equal because we can let it, we can assume its direction is towards the right hand side, positive x direction. So then it will have the same direction as presumed FJE, right? So these two forces will equal to each other. They will equal to each other, okay, in terms of magnitude. And then once we have all this relationship, we can write we can write the spring Hooke's law in this spring into one equation, which is actually this equation. And then we actually put the F, this force, to replace P, okay? Then we get this. We have Fj. There are two equations, but they are they are equivalent. First, the Fj, that is on the right hand side. Fj equals to spring constant times Uj minus Ui. I rearranged it, but it's actually Uj minus Ui. And as I mentioned before, we rearrange it because we want to write it in terms of matrix, right? So that's why we write Ui first and then Uj. And then force Fi on the left-hand side, note, is the spring constant times Ui minus Uj, because that is with respect to the point I, to the node I. So then with Ui minus Uj. These two are equivalent because Fi and Fj is the inverse of each other. Ui minus Uj and Uj minus Ui also is inverse with each other. If you multiply -1 to any of the equation and then add them together, they actually equal. They are exchangeable, right? In this case, we write it for those equations for each node, and then we can extract the k now. Now we can extract the k and extract the u. So we will have this matrix k minus k minus k k. You have this matrix times displacement vector equals to force vector, right? This is very beautiful. This actually extract the key point of these two equation set on two nodes. Do you guys follow me? Yeah, excellent. Now, once we extract this, then using the mathematical review we had before, you can write this matrix into this form, right? So here K is bold, means this is the matrix. Here you see we write it in the non-bold way. This is a scalar, spring constant scalar. But this spring constant can become a spring constant matrix. Then it's bold, okay? This matrix times displacement, U. Displacement can also written as Q, bold Q in the parentheses. This in bold means this is the vector. And the force can also be written in the bold form in the parentheses. That means it's the vector, it's the force. Now this can be written as K dot product Q equal to F. This Q represents the displacement, but it has it can have another name. That name is called degree of freedom. Degree of freedom means how much this Q change in different dimension. And then what's the change value there? Okay, those are represented by the displacement. The dimension actually here is two dimension, x and y. No, this is actually one dimension. This both in x, but two different nodes. If you have a 2D question, then this Q will be 4 by 1 vector. You will have UI, UJ, VI, VJ. If it's 3 dimension, we add 2 more rows there, WI, WJ. Okay, so that is called degree of freedom. In each different dimension, how much you can move. and in which direction. Okay. So K is called the stiffness matrix. This is the important name, very important, stiffness matrix. Q is vector of degree of freedom, Q. F is vector of element force. Element force means the force found on the element node. Okay, it's different from external force. But if there are external force applied here, they can be added into this equation. Okay. And for the stiffness matrix, last class we very briefly talked about it. Now we can discuss about it in detail. For the stiffness matrix, it actually has quite a lot of important properties. Firstly, it is a square. It is square. The reason is because the number of the force and the number of the displacement on each spring, they are the same because each node has one force, one displacement. So force and the displacement are the same. Then it results in the stiffness matrix the same, right? Because here you see the raw number of the stiffness matrix actually equals to a raw number of force. Raw number of force equals to a number of force. Column number, how many columns there? Matches with the number of displacement because each column, let me join here. So here you need to be very clear about what is column, what is row. Here we can use this as an example. Column number is this. You have column number 1, column number 2. That has to be matching with displacement number. Displacement number 1, displacement number 2. Okay, column number. And then they will give, they multiply together, give one force. And then if you, that's what I'm saying, that the column number corresponding to displacement number. And then raw number corresponding to the force number. Because this one will give, this one times this will give this. This one times displacement will give this. So how many raw you have in the stiffness matrix corresponding to how many force you will have there, right? And for this case, for this spring, force number equals to displacement number because we only consider node there. So that's why stiffness matrix always have the same number of raw and column. Okay, so this is a very important point. Okay, good. Now, second property is this stiffness matrix is symmetric. It's symmetric. The reason is as we discussed, we actually multiply the -1 there, right? For the right-hand side node and left-hand side node, we multiply -1. So for this 2 by 2 matrix, they become inverted, and then they actually form a symmetric matrix. Symmetric matrix, right? Means around the diagonal, the value is not changed, but off diagonal value equal to each other, right? Symmetric. Right? We also previously discussed the asymmetric or antisymmetric, means across diagonal, those elements are actually the inverse of each other, right? So this is a unique property of stiffness matrix of a single spring. And also this is a singular matrix. The reason is also, as we just discussed, those equations are actually not independent to each other. They can merge together to be one equation because each spring only have one Hooke's law, right? One Hooke's law gives one equation. So here we just write that into 2 by changing the format, right? So itself, this matrix itself is a singular, and its determinant, if you calculate its determinant, actually equal to 0, and it cannot be inverted. The whole matrix cannot be inverted. Okay, and also this is the positive semi-definite. Positive semi-definite. We discussed about this concept before. Very important concept. Here it says semi-definite means it's actually equal to 0. The determinant equal to 0. It's not larger than 1, larger than 0. It's equal to 0. Okay, but never less than 0. Never. So that's a very important property as well. So these are the key properties of a stiffness matrix. You need to get familiar with it. Okay. And observe here are some observations for any given node displacement. Node force actually can be calculated by this equation. So we show this equation already. If we know the displacement here, and as we already know the spring constant, then they multiply together can help us to get the force on the node. We can get it. But if we don't know this, and for any given node, if we don't know this, we get this force. We only get the force. Then this value cannot be uniquely determined. They cannot be uniquely determined. Okay, because the reason is because if you have force applied to the spring, like this spring, if we don't know the displacement, okay, we only know the force, Fi and Fj we know, spring constant we know. If we only apply the force here, then depending on the force, this displacement can be any value, but the difference of the displacement that will give the deformation of the spring. That is no. But the exact value of displacement, that can be any other value. Okay, because they all can be added with any delta, any net displacement. Those net displacement get vanished when we subtract ui from uj. Okay, but the net ui and uj do not know. So that's that's the observation we have for given node force. If we have the force there, node displacement cannot be determined uniquely. Uniquely, we can only determine the net change of the spring, but we don't know we don't know the ui and uj. But that is the concept that has to be very clear. But this is only for one spring. If multiple springs connected together, and they are also having connection with rigid wall, then this ui and uj actually can be determined by having many equations together. You can still determine that. Okay, so make sure yourself understand all those properties. Those are very important key concepts you need to understand to have a solid foundation of a finite element. Okay, now do you guys follow me? Yeah, excellent. Now we have explained single spring now. Okay, single spring we know now. Now is the time we get into that 1D system that consists of multiple springs now. We need to understand that now. And let's solve all the unknown we discussed there based on the nodes we have. Now, we already write the connectivity table in the last slides, previous slides. Now we start to treat whole system using this equation. K times Q equal to F. We already treat one spring with this equation, but now we can start to treat the whole system with this equation. We first write the K, that it equals to K times Q equal to F, right? K is the spring constant. So you have the K, right? You first would write, put all the K as 0, okay? And then we will add the number in by analyzing spring by spring. All the K equals 0. And then times the displacement. That displacement actually comes from the node, as we said. We have a node 1, 2, 3, 4, 5. We have 5 displacement within the whole system. And correspondingly, we have 5 force on node 1, 2, 3, 4, 5. So we have 2 vectors, U and F. Spring constant matrix times this displacement equal to the force. Here we have expanded to the whole system now. Okay. Now in this whole system, we can fit in the equation we have obtained from each equation individually. They all can be linearly superimposed. Okay. So now first equation for the first equation set for the spring number 1, that is it has this spring stiffness matrix. It has a U1, U2 because it has node 1, node 2, U1, U2. It has a force F1, F2, right? And it has and here 1 in the parentheses, in the parentheses. That is means we are dealing with force on the spring number 1, element number 1, right? Spring element number 1. We have this one, and then we can put it into this this global format. We put a K1 minus K1 into here. As I said, they are actually corresponding to the rho, to the force, right? The rho, this rho actually corresponding to force, column, and the column corresponding to displacement. So we put this U1, K1 minus K1, we'll put it here. And then this minus K1, put it here. U1, U2, they belongs to here, U1, U2. Force F1, F2 belongs to here, okay? This is the force only regarding to this spring, okay? This is super important, this is a key point. Make sure you do it after the class, you do this by yourself, and make sure you can get the same results. This is the super important fundamental practice, okay? Once you are able to do it correctly, then more complex question you can also handle in similar manner, okay? So this is the spring number 1, we added now. Now we deal with the spring number 2 in the same manner. We can do it in the same manner. For the spring number 2, we know it has a U2, you have U2 and U4, right? U2 and U4. But you know, spring number 2 connected with this rigid body. If this rigid body has one displacement, that displacement actually is shared by spring number 1, spring number 2, and spring number 3. It's shared, right? So the U2, the displacement of U2 here for the spring number 2 actually is a sin 1 U2. Okay. But here, spring number 2 has a force here. This force is not equal to this force. It has its own force. Number 2 has its own force. So when we add number 2 force to this column, they should be added together. Force is not shared. Displacement is shared because of this rigid node here. Okay. Now, for the spring number 2, we can use the same equation. Here we just change it K1 to K2, right? K2 minus K2 minus K2, K2. And then U here should be U2, U4, because that's specifically for element number 2. And then force is the F2, F4 with the 2 in the parentheses, right? So then we get this guy. This is number 2, spring number 2. Do you guys follow me? Yeah, excellent, excellent. Very good. You guys followed very well. So this is the super important part. Now you know you follow the same way. Write spring number 2. Once you write this, you can add this one into the global format. You will add K2 minus K2, K2 minus K2. Here you see they are in the row number 2, row number 4, right? Because this row number 2 will be multiplied with U2, U4, or row number 2, row number 4, also column number 2, column number 4, because they will multiply with this row will multiply with this displacement vector to have a corresponding UK2 times U2 minus K2 times U4, right? K2 is the same, the spring constant. U2, U4 is the displacement on the both nodes 2 and node 4 for the spring number 2, right? Same thing for minus K2 minus K2 times U2, U4, same thing, just add the reverse. Then they equal to force here, F2 and F4. The blue part is the matrix format of spring number 2. Okay, so now we consider the 2 spring now into the system. That's not sufficient. We need to consider all the spring, all the elements, right? So now we continue to the spring number 3. So for number 3, we can write it in similar way. So you see, once we get familiar with how to write matrix matrix times vector format for any individual spring, then it becomes conventional. We can quickly write for any spring. Just to make sure you follow connectivity table. Don't make those symbol messed up. Okay, follow that sequence from left to right, and then make that table carefully, and then you can write this without any question. Once you have this for spring number 3, you add into this global format. They can be linearly imposed, superimposed. Now you have here the red one are the spring number 3. Okay, red one. So you see displacement are shared on the same node. Force are summarized together. Now follow the same manner. We do the spring number 4. Now we have a purple color. So you see spring number 4. It has nodes number 1, number 3, right? So they are in the row number 1, row number 3, column number 1, column number 3, right? By itself is the symmetric matrix, and then they are positioned to be added. The position to be added into the global matrix actually is following their node number. Like that's why the connectivity table is very important. It avoids any impossible mistakes. You have a number 1 and a number 3, node number 1, number 3 add in, and then displacement no change. They are shared. Add the force, the corresponding force on the springs at both ends. Okay, so then we have a spring number 4 solved, and then also we can continue. Spring number 5, we get this green one. Okay, so get the green one added in, and then finally number 6, spring number 6, that's in the brown color. It's brown color. So then added in because it's in it's number 6. The node is number 4, number 5. So they are in the column number 4, column number 5, and the row number 4, row number 5, and then the corresponding force added together. This is the most important equation you will get. Most important. Once you have this, you can check whether this is correct or not. Okay. One way to check is look into this spring global spring matrix, see whether this is the symmetric, because every single spring stiffness matrix are symmetric, and they are added in a symmetrical way into this global matrix. So eventual results is also symmetric. If you find this is not symmetric, then something is wrong. Here you see around the diagonal, -1, minus K1, minus K1, minus K4, minus K4, minus K3, minus K3, minus K2, minus K2. Across the diagonal, they are all symmetric. That is correct. Okay, that's one way to check this is correct or not. Another way to check is make sure you don't miss any force here. Those in the force vector, each row corresponding to one node. You can check in each node whether the force you added here, they are coming from a spring, right? You can check whether those force are complete or not. This is the node number 1, which is on the wall here. You see my cursor? You see my cursor? Yeah, good, very good. You see this node number 1 here, the wall. It has the connection with the spring number 1, spring number 4. That's why you have 2 force applied here. 2 force applied. This force will be balanced with the reaction force here. But here in this table, only we list the force that is exerted on the spring. Okay, so then we have F1 plus F4, F1, F4, right? They have a subscript 1 here. That means it's node number 1, node number 1. Okay, and then the parentheses is the spring 1 and the spring 4. Okay, and node number 2 here, you see, have a node number 2 subscript, have a spring 1, 2, 3. So you check it here. Yes, it has spring 1, spring 2, spring 3. That is accurate. And then this force will be balanced with F2 external applied force. Okay, we didn't put it here yet, but they will balance with this force. Okay, so after checking both stiffness matrix and the force vector, then you will get certain that we have successfully constructed the global matrix now, global matrix format. Now, next we can start to solve them. we put the no value in, we can solve it. So to solve that, we will use the relationship we will relationship that the element force and external force actually equal to each other. They balance with each other. So external force is the capital one, Fi. For any node, you see node I, you have a Fi applied. And then you have all the internal force from different spring E, right? E from 1 to IE. How many number of spring here? All on this node I. They are adding together equal to 0. Here this actually they minus each other. They actually equal to each other. They equal because they are assumed in the positive x direction. So we put it external force equals to internal force summary is actually equal to 0. This one. Here I equals to 1 to ND. ND is node number. Okay. How many node? And we have how many summation of the force in each node. For example, for the node number 3, this one, node number 3, you have a spring 3, spring 4, spring 5, and external force F3. So all these 4 forces added together. So for the spring node 3, you have this one, node number 3, spring 3, node number 3, spring 5, node number 3, spring 4, and then external F3, big force, capital 1. Okay. They added to the F3 minus these 3 force equal to 0. Okay. Then this means F3 equal to this summary. And remember, in this writing, we actually add all the force together. That means this force, this internal force, actually can be written as the external force as well, because they are the same, right? So here, this 3 value actually equal to F3. Sum of these 3 value equal to F3. So here, you see this one can be written as F3. In the same manner, this is a very good convention. In the same manner, you can write the force on the node number 1. That is reaction force, R1, coming from the wall. Node number 2 is the external force, F2. This one, F2. Node number 3, F3. Node number 4, F4. Here, you have F4. Node number 5 is reaction force from the wall, which is here. Okay. So right now is 140. We can continue these important materials in next lecture. Today we went through the important derivation now. Make sure you practice it after the class. Then you will master this important skill. Okay. Very good. Thank you.